Hello once again, here is Skip, Victor Echo 6 Bravo Golf Tango with another installment of my little 10 Ghz experiment. In the last video I got the stand built up and the dish mounted in the garage, so next was to drag it outside, get things hooked up and see what it would do. After rolling the dish reflector outside, I tried to lift it up by hand like we did in the garage, but it was just too hot, so I put the old Jeep crane winch together again and used it for lifting. It was at this point I saw that I had the winch line on the wrong side of the square mounting frame. I thought of lowering the dish down and rerouting the cable, but I figured I could bolt it together and it would hold in place with the dish leaning up against the gym poles of the winch and eventually get it all mounted together. So the winch line out of the way, I tightened down all the bolts that are holding the reflector frame to the dish mount square frame. All good to go. Now to get the old Jeep out of the way so that I can start installing the feed mount and the feed mount arms. This homemade crane that I've built for this old Jeep has been the handiest thing, as I've said before in other videos, and I couldn't have done a lot of this without it. Oh, kind of got ahead of myself. I guess the next step was putting the actuator on for the elevation lift for the dish. Easy enough process. Working on a small dish like this compared to the big one is quite simple. It was definitely a beautiful day for doing this work. The temperature was right around 27 degrees centigrade and nice clear skies. Nice little breeze to keep things cool. Bolts are all tight, everything's looking good, so it's on to the next step. I didn't bother making a video of installing the dish mount and the arms. It's pretty straightforward, and it was pretty well covered on the previous video of the assembly being built in the garage, so this is what it looks like. Besides the giant hole in the center in the middle of the dish, this old surplus dish had quite a few smaller holes all over the surface, so I covered them over with a tinfoil tape to prevent ground noise from leaking through the backside for this test. I wired up the motors to this old ICO variable power supply. The idea was that I could lower the voltage down if I wanted the motors to go slower or up for go faster, and made up this simple switch plate to control the directions up and down and left and right in azimuth. Earlier I did get around to downsizing the whole feed assembly onto a smaller plate so that it would fit into the small 4-inch mounting bracket of the new dish. This picture here shows it sitting in the bracket of the new mount. It slides back and forth and uses a small C-clamp to hold it in place for adjusting it later to get the best optimization. So getting the whole dish put together and ready to go took a better part of the day. So I waited till the following day to set up the rest of it and finally get around to doing the solar tests. So here's a grand tour of the setup before we get into it. Back side of the dish, you can see the tinfoil tape on all the holes covering it up, and all the cables, etc., going from different parts of it over to where the receiver and the noise meter is. The radio is an old Kenwood TS-811 432 rig. I more or less just have it there to terminate the end of the receive line. The noise meter, which is on the 432 IF coming from the transverter, is simply teed into the line. There's 12 volt supply there in the middle that runs the transverter and a preamp, and then the old ICO supply on the right hand side, which is for running the motors. Right there you can see how the noise meter is teed into the coax line that's coming from the transverter. Then the rat's nest of cables go across the ground, up the stand, taped up to the dish support arms and around the edge of the dish and up to where the feed assembly is. Sorry for the wobbly video, but it's hard to walk around with the camera in my hand and keep a steady shot. So, wanting to get into doing some testing, I started moving the dish around and discovered that to have the motors go slow enough to lower the voltage, the actuator arm didn't have enough power to lift the dish up. So I had to add some counterweights to give it some assistance. So finally got things moving and started moving the dish into position. I was just using the shadow of the feed against the back of the reflector to tell me where I'm at. That's nothing else here to give me guidance. And of course there had to be quite a gusty little wind, which was going to make things difficult because my azimuth motor does have some slop, but we'll get by. So we're almost in position, and I did start finding some noise detection after a bit of going back and forth. At first I got all excited because I thought I was on the 20 dB full scale range, and I thought I was seeing like 16 dB of noise. But then I came down to earth and realized I was only on the 10 dB scale, so a little more realistic. The clicking that you hear occasionally is the switches I'm activating to adjust the motors, the azimuth and the elevation, to try and get a peak. The darn wind was moving the azimuth around quite a bit, and it doesn't take much for it to drop 2 or 3 dB at the most sometimes with slop in the drive. So for the first detection, I was getting close to 8 dB of noise detection from the cold sky. I was expecting more, but they were not done yet. So this is a lot easier to do on this small dish compared to the large one. The trick now is to adjust the feed position to the focal point and optimize it for the best signal. Like I said before, this is a relatively simple task compared to the big dish. I just merely had to take the ladder and go up there and adjust it. I would mark the position with a marker pen, then move it ever so slightly, maybe an eighth of an inch to a quarter of an inch at the very most, and then keep checking the noise to see if there's an increase or a decrease, to find out which direction I was going. The neighbor's puppy sure was making a fuss. I'm not sure if he was barking at me or a squirrel. So this was the first adjustment. There was 10 in total, and you can see the slight increase I'd had with this first adjustment. So we increased it by about half to 3/4 of a dB more from the first initial detection. As I said, there was about 10 different positions I adjusted on the focal point, and this is the fourth position, and you can see the increase I've gotten so far. So right around about 9.5 dB increase. So this was position number 6, and it's the winner. It took some struggling to get up to it. The wind kept moving me around, but it finally got there. I moved the feed about 4 more times after this, and it just progressively went down from there. So this was the optimized spot for the best position for the signal detection. We're getting there. Just be patient. The reason it takes so long to peak anything here is the combination of the wind bouncing me around, and the motors are just turning way too fast. I've lowered the voltage, but it was just hard to handle. One thing I've learned on this frequency is that the mounting and the motor drives have to be tight, very tight. You just can't have any slop. So finally it peaked out about 9.75 to 9.8 dB increase of solar noise. So with the solar test with a small 6-foot dish done, which of the two dishes is better, the 6-foot or the large 21.5-foot mesh dish? The comparison between the two dishes is kind of strange in a way. When I did this solar test with the same feed back in May with the 21.5-foot mesh dish, I was also seeing a peak of around 9.5 dB increase of solar noise over the cold sky. With this little 6-foot solid dish, I'm also seeing in the same area of 9.5 to 9.7 or 9.8 dB increase. There is one variable, though, between all these tests that is going to make the big difference. When I did the solar test with the 21.5-foot mesh dish, the solar index was an area of 175. I remember it being one of the highest numbers I've ever seen. When I did the solar test with the 6-foot solid dish just the other day, I checked the solar index and it was only in the area of 93. So I took these numbers and took the VK3UM EME calculator and manually inserted the solar flux index for 93. I then adjusted the LA input loss adjustment so that I would get a solar noise measurement of 9.7 dB to have it equal out to what I was seeing just the other day. Now with the calculator set to show me what I was seeing just the other day of the solar test with this little 6-foot dish, I then changed the solar index to 175. I was hoping now the calculation would give me a more of a equal comparison of what this little dish would do compared to the big dish if both were at the same solar flux index. And back then with the big dish it was 175. So now with that set, this little 6-foot dish is now showing me a calculated solar noise measurement of 12.27 dB. So if I've got this set up correct, what this is telling me is that the little 6-foot solid dish, being much more efficient, is showing me 2.77 dB of an increase more than what the 21.5-foot dish would see if the solar flux index was the same for both tests between the two dishes. Really? But I'm doubtful. The more I think about it, there's just too many variables that are unknown for the VK3UM program. The different losses here and there, and the only way I'm going to resolve it is I'm going to redo the test on the 21-foot dish and plan it around a day that has the same solar flux, or very close to it, to the one that the little 6-foot dish was done on. And then we'll see. So here it is, August 1st, and we're going to repeat the test on the big 21-foot mesh dish to see what the solar noise is, with the solar flux index now being at 94. So I got the feed reassembled. I got it mounted back on a dish and track the dish back up towards the sun again and back into the shack to take another measurement. So I got the dish steered off the sun, or more or less what we call cold sky, and got the noise meter zeroed out to start doing the recording. I then flipped it into auto tracking and let it slowly come back onto the sun. This little video gets to be a little long, but I didn't want to edit any of it out, and it took some doing to finally get it to peak out, so we'll get there in not too short order. Okay, this is when the auto tracking peaked it, and now I'm going to bump the offsets for the auto tracking and peak it a bit higher. And again, the resolution on the elevation actuator is just too coarse. I have a hard time getting it to peak on. It'll go up to it and go past and then back and forth, so it took some doing. It looks like I'm going to get it to settle in here a little bit, so we're getting close to what's going to be the maximum. I was actually kind of surprised to see it get this high. And this is where I'm going to call it quits. I say it's maxed out here, just a hair over 8.5 dB. We'll say 8.5 just for round measures, and call it good. Well, the results of the two tests are as fine as frogs' hairs. I find this rather interesting. The earlier test in May with a solar flux index of 175, the noise peak was 9.25 dB. Today's test with a solar flux index at 94, noise peak 8.5 dB. That's a difference of 3/4 of a dB. I would have thought it'd be a lot higher, a lot more different, or farther apart with such a huge difference with the solar flux numbers. Okay, the little dish is still more efficient than the big one at this frequency, but with the new data or the numbers, just how much better is it? Sort of what the VK3UM program told us. So okay, here are the numbers. Both dishes with the same solar flux index number. The small 6-foot solid dish was peaking out at 9.75 dB, where the large 21-foot mesh dish was at 8.5 dB. So the small dish has an area of 1.25 dB gain over the large dish on detecting the solar noise signal. Okay, the VK3UM program calculated it should be around 2.77 dB, but my test here isn't perfect, and there's variable small things that are a little off. So this is close enough, I would say, and it does show you just the efficiency of the little dish over the big one. At least I think it is. Anyways, find it very interesting. So this little 6-foot dish would work well for working the moon on 10 gigahertz. The only bad thing about a small dish like this with a prime feed is the blockage. My feed mount up there is quite small, and have to hang an amplifier up there and other goodies. It could get large, so it's not perfect for that. So the better dish would be an offset feed. So maybe we'll test that next. You never know, so stay tuned.